All right, welcome back, class. So this is part 2, continuing on with sewer design homework. We just finished step 1. Okay. So again, we just calculated our flows here based on the information given to you. So this is my Q initial design flow. This equals Q initial. All right. So now let's go to step 2. All right, determine the slope S between the point we want to connect manholes. Vertical distance fall, and the delta is a change in vertical distance, okay? So now we're in step 2, so we got to calculate S. Okay. Step 2, okay, S equals delta H over delta L. Okay, where do I find this information? Okay, if I go to the homework problem, so here's step 2, again on this flow chart. So I went from step 1 to step 2. I go look at my sewer design homework. All right, so from manhole 1 to manhole 2 is 20 meters. From manhole 1 is my height, and the top of my manhole at manhole 2 is 19 meters, and my distance between those two is 755 meters, okay? Again, from here to here, manhole 1 to manhole 2, that's my reach, okay? So if we go back to here, so we have 20.00, let's double check, okay? Meters minus 19.00 meters, and my length is 755, and that equals, so 1 divided by 755 is 0. Let's see, 0.00132. Okay, so that's 1.32123. 0.132. So that's 1 meter of change in 755 meters. Just make sure I'm reading my calculator correctly here. So 0.00132. If you can have 3 sig figs, your answers will be pretty close. Okay, so that's S from step 2. Okay, so now I know my slope of my ground, right? So I want to, remember in sewer design, I want to follow my slope. Okay. Okay, so where did my step 6 go? Let's do, I must have accidentally shut her down. Okay, step 3. Okay, I went from step 1 to step 2. Based upon Q initial design flow, Q initial, use Manning's equation to calculate minimum required diameter, D min. Step 3. Oh boy. Step 3, D min. Okay, knowing the initial design flow and slope using Manning's equation, find the minimum required diameter, D min. Remember, design flows are based on the pipe flowing full. So what I did is I rearranged the Manning's equation to find that. This is the English system. Here's the metric system. Okay, so step 3, I got to find my minimum pipe diameter based on my slope and my calculated flow. Okay, step 3. All right, so if I go back to my document cam, okay, D min equals Q times Manning's N divided by 0.3117 times the slope to the 1/2. So remember, this is all over, and this is raised to the 3/8. So I'm basically, I did the algebra for you. Q times N over 0.3117 times s to the 1/2 raised to the 3/8. Okay, so if I plug and chug, my minimum diameter equals Q is 0.233 times 0.013. My Manning's N number is where? Remember, it's from the homework problem. Right here. Okay. All right, so we're back to divided by 0.3117 times my slope, 0.00132, raised to the 1/2, and then I got to raise this whole thing to the 3/8. And because I've done this many times, I get equals 0.609 meters. Now, okay, according to the problem, pipe sizes are multiples of 50 millimeters. Okay, all right. So that means I don't never want to round this down, so I want to round it up. So my next pipe is my round up equals 650 millimeters, or 0.650 meters, right? So that is my minimum pipe diameter. So, well, it's this, but remember, I got to round up. So this is my design now, okay? So that's step 3. Boy, that's a horrible 3 there. All right. Step 4. Select the next pipe size, D new, that is typically manufactured and is larger than the diameter than D min. So this is, so right here, so I'll go back to this is now step 4. Okay. Next size pipe. Okay. Okay, so as you see, I'm following the arrows here. So let's go back to the slides. So step 4, okay. Knowing that the minimum required diameter D min, select the pipe D new that can be reasonably obtained, that is larger than the diameter of the minimum. In general, do not select a pipe smaller than a pipe coming from the previous reach. Yes, because the pipes have to get bigger. So this will make sense as you go further down. Step 5, now re-enter the new pipe diameter D new and area into Manning's equation to determine the actual flow capacity, Q new. Okay, so step 5. So we got to determine Q new. Okay, so if I go to here, because we upped the size of this pipe diameter so we can actually hold more flow than this. Okay, so but we need to know that. Okay. Step 5. Q new equals, okay, and if I go back to my slides, I do believe I did a short Q new English. I just basically, so we don't have to calculate the hydraulic radius and stuff. I just did the math for you. So that's 0.3117 times the diameter 8 to the thirds times the slope 2 to 1/2. And we divide that whole thing by Manning's N value. Okay, so if I go back, all right, so 0.3117 times my diameter is, remember this has to be in meters, Manning's, 0.65 raised to the 8 thirds times my slope is 0.00132 raised to the 1/2 divided by 0.013. 3. Okay. And our Q new equals 0.276 cubic meters per second. Okay. Because my diameter is bigger than what I calculated, that means my Q new better be larger than my Q initial. Okay. So that's my new velocity. Okay, so now, because reason why we need to do this, because we're always assuming the pipes are flowing full in our analysis. Okay, all right, so now let's go to, okay, so that's Q. All right, so now let's go to step 6. Using Q new, because we need this Q, calculate the velocity within the pipe V. Okay. All right, V equals Q new divided by A. All right. Okay, so with that, so step 6. Okay. So remember, here's step 4 up there. We're rounding up. Step 6. Okay, V equals Q new divided by area. Okay, so that equals 0.276 cubic meters per second divided by pi times 0.65 squared divided by 4. That's the area of a circle. And then I get 0.832 meters per second. Okay? All right. So now, step 7. So let's go back. So step 6, so as you can see my flow areas here, recalculating new flow Q new, use the dune diameter and an area into, that's step 5, so a new Q new, okay? Now, step 6, calculate the velocity within the pipe area using D new and resulting Q new, okay? Step 7, velocity meet requirements, yes or no? All right, so what are, what are our velocity requirements? Okay, our required velocity is, the velocity has to be greater than 0.6096. Is it greater than 0.6096? I get 0.832, that's yes. Is it less than 3.04 meters? Yes. So our velocity meets requirements. Yes. Okay. But what happens if it doesn't meet velocity? No. Recalculate another Q new based on a new velocity V new. Okay, what does this mean? Okay, so say I am, so if I don't meet velocity, say I am small, I'm less than the minimum velocity. Okay, I'm less than a minimum velocity. So I am like at 0.5. So what I do is I set my V to equal 0.6096, okay, and then I recalculate a Q new. And if I'm over 3.04, say I'm at 4.0, I set it down to 3.048, okay? So let's go, so, okay. Step 7, check the velocity to be sure it is between 2 feet per second and 10 feet per second. So this is the English version. All right, I give you the metric version on the homework problem. Okay. If the velocity is not in the proper range, if V is less than 2 feet per second, set V new to 2. If it's greater, set it to the maximum. Okay. Step 7a, then we calculate a V new based on a Q new. Okay. All right. So A times V new. Okay. So now I have the A changes, or the A is the same. So we just, our new velocity is going to, so some reason my computer's going, maybe I'm going too fast. So area is known. We set it to the new velocity based on the minimum or maximum. Now I calculated a Q new again. So this is a second Q new, okay? So if the velocity is not in the proper range, insert the new flow. So now that we insert the new flow from the V new into Manning's equation and determine the new slope, S new. Okay, so here we go. I rearranged the equations for you. Okay, there's metric. All right, so now let's go back to our flow chart. All right, so velocity means square root. No, put in the required velocity, calculate a Q new. Step 7b, calculate a new slope. So if you look here, 7b, right? Here's the arrow. Now look where 7b goes. Does the minimum pipe have ground cover? Okay. No. We go back to step 2. Okay. What happens if it's yes? I'm missing my arrow here. If yes, we go to step 8. Where's step 8? Where did step 8 go? Ah. No, back. Where's my yes? So I'm something happened here. What's going on here? I should have something's missing on here. Something's not showing up quite right. Okay. Oh, here's step 8. Okay. If it doesn't, then we go back. Okay. So I didn't put a complete sign. Okay. Sorry about this. All right. So if it doesn't, now we go all the way back to step 2, and then we go through the whole system until we hit yes. Okay, if this is yes, then the design is complete. Okay, so basically that's how we use this. Recalculate. Okay, so all right, so we met velocity, so we are on velocity meets requirement. Does the pipe have minimum required ground cover? So we got to answer that question. So this is all right. So let's go back to. I'm just going to pause this for a second to make sure I'm not telling you something incorrect. Okay, I just had to scroll up. Sorry about that. So, all right, so we calculate a new velocity, calculate a new slope. Does the minimum ground cover is required? Yes, design complete. If not, we go all the way back to step 2. Okay. And then we go to step 9 if we don't meet, because then now that the slope changed, now we have to calculate another Q. And based on S and D new, and again, then we go all the way to here to step 6, check velocity, step 7 if it meets, and go again, okay? So if we have a no, basically you follow the dash arrows, okay? All right, okay. And if we have a yes, we stay on the solid arrows, all right? So this is how this works. I really apologize for that. All right, so what's minimum pipe have ground cover? All right, so let's go back to my document cam. All right. Okay, so with that, let's zoom up. Okay, so manhole 1. So where do I find the elevation is? Elevation 20, okay? So what I'm gonna do here is I'm gonna draw a picture, then I'll show you my diagram here. Okay, so this is 20.00 meters, okay? And then manhole 2 is elevation 19.00 meters. Okay, so my minimum code is 20 meters. Okay, pipe thicknesses are 25 millimeters. And so we met the minimum pipe diameter, which is 200 millimeters. We're at 650 millimeters. All right, all pipe crowns must match manholes. All right, so, okay. So here we go. So this is how we're going to start. All right. So we know we need a minimum of 2 meters of cover, right? So if I come down to here, I'm going to zoom this in here. So we can see here. Okay, I mean, when you do your profile sketch, I would like this, if you can do it in AutoCAD, great, or Civil 3D, but very nice and neat. I'm just sketching here. All right, so so minimum ground cover, 20 meters minus 2 meters is what? 18 meters, okay? So I have a pipe thickness of 25 millimeters. So if I grab my calculator, so 19, let's see, 20, so 18 minus 0.025, that's 17.975. So this is 19.795. That's the top of pipe, or that's it. This is my crown now. So right here is my crown. Okay. So here's the top of pipe. This is my crown. This is top of pipe. Okay. So now my diameter was what? So this is 0.65 meters, correct? So my invert is, okay, so 17 minus 0.65 is 17.325. 25. Okay, that's my invert. All right. Okay, so now, okay, so and then I have my bottom of pipe. Okay, bottom of pipe. Okay, so now I subtract 0.025 because the pipes. So this is 17.300 meters. So these are all meters. Okay, so in a profile, in a plan and profile like I was showing you, typically what they do is they put rim elevation, which is the top of the manhole. They provide you with the invert elevation, and then they provide you with the diameter of the pipe, inside diameter, right? Okay, and then what they do is they provide a slope. Okay, so now what I need to do, so this is manhole 1, this is manhole 2. So now what I need to do is I need to project what elevation will my invert be 755 meters away. Okay, so basically I want you to look at that plan and profile slide, and you've done this before in Howard's class, and make sure you know this. Okay, so I know the top of pipe is at 18 meters. So 18 meters times 755 meters times my slope, right? Times 0.00132. So that is, so my top of pipe is 17.934. 0.934 is top of pipe. Okay? Now, 20 meters time. Let's give me a second here. I'm gonna pause again. You're good? Okay, I'm recording. All right. Okay, so I made a mistake here. All right, so we got it. We know we got to figure out how much distance. So let me back up here. So 755 meters times 0.00132. So that means I drop 0.9966 meters. Okay, in 755 meters. Okay, so I got to subtract that from 18 meters to get me my new top of pipe on the other manhole. So that equals 17.003 meters. All right, so I'd say we're close enough for pipe, okay? So my crown minus 0.025 equals 17.028. There's my crown minus 0.65. My invert on this manhole is 17.678. Okay. And that's not right. Hold on here. Let's take 755 times 0.00132. Okay. And I'm going to subtract the invert of 17.325. And that should be 16.328. I'm just throwing numbers in my calculator all wrong here. I apologize for that. All right, so this is actually 16.328. All right. Okay, what I want for your diagram in the end here is a profile. Okay, so I want to see at least the invert. Check your covers. Okay, so this is 2 meters. This is 2 meters. The more information, the better, right? Here's my invert. I can show my bottom of pipe over here, right? The key is you need to show inverts. Okay, invert. So my invert for manhole 1 is 17.325 meters. My invert for manhole 2 is 16.328 meters. And then I want to check my cover. So how do I do that? I take 755 times 0.00132, and that gives me my distance that it falls from manhole 1 to panel 2. Okay, that gives me my top of pipe. That way I can check it. Okay, so very nice, neat diagram. Okay, so that's how I did the first reach. Okay, so now if I go back and let's just look at the problem, I just designed reach 1 for manhole 2. Okay, so now how am I gonna? So now I can design the reach for manhole 2 to manhole 3. Okay, so the first thing I need to do is find the Q initial from area 2, area 3, and area 5. Here's area 5. Here's area 2. Here's area 3. Add the infiltration. I calculate Q initial. Okay, then I'm gonna add Q initial from area 1, not Q new, Q initial, because otherwise we're going to over design it. Q initial from Q1 goes in addition to these flows here. Okay, that's important because otherwise our diameters, believe it or not, will get really big. So when I'm going to the next reach, I add Q initial from the previous reach and add it to the flow for the next section of pipe. Okay, and then moving forward. So if you want to make a spreadsheet, however you want to do it so you can check your work, I provided the answers in Blackboard. So if I go here, here's the flows, here's the design solutions. Okay, so if you look here, if I open this up, as you can see here, here's all my flows, so you can check your work. That's that. And then here's the design solutions. Okay. So remember, you want to match crowns. Okay. Match crowns. So what does that mean? All right. So let me go back to this crown. All right. So I know my crown is 17.028. Okay. So that means the crown going from manhole 2 to manhole 3 is 17.028, and the type of pipe is same. So now my invert, this is from this point down is when I can calculate my new invert, because I have to match my crowns. Okay, match my crowns. All right. Okay, so just want to make sure I didn't miss anything. Match crown elevations. There's a little thing you can read about it. All right. You can kind of see how they create. They'll put PVC in here when they cut the manholes. They create these nice slopes here, so any water that when it flies, so they'll take these out, so when the water comes in, it'll actually flow through the next pipe. Here's one that has 3 different diameter pipe. So sometimes, so see here, these two are matched. This is the main flow, but then we have this other guy. So obviously this crown isn't matched, so sometimes we have to do something a little bit different. Okay. So the reason why we want that is to prevent, they call it a hydraulic jump. They want to maintain a smooth flow. If we change the crown elevations, what happens is we want to keep the flow consistent. Otherwise, if we disturb the flow, that's when things get plugged up. Step 9, if pipe does not have minimum required pipe cover, determine a new slope to achieve cover from step 2. Calculate Q new using new slope. S and D new required determined from step 4, and repeat the design process from step 6. Okay, so there's the flow chart, there's your homework. So hopefully by using the equations in the PowerPoints and this will help you get through the design process. Okay, so that's all I have for you for now. Sorry about the confusion. Good thing you can fast forward and rewind and all that good stuff. So I will attach this in Blackboard and you can start working on learning Plan 6.